I want to start today by talking a bit about context switching.
Oh yeah, the absolute enemy of focus.
Right, because, we all know that feeling when you are trying to do, well, too many things. Imagine you're trying to read this incredibly dense novel, and at the exact same time, you're updating an inventory spreadsheet and trying to answer complex questions from your boss.
Eventually you're going to type a line from the novel right into the spreadsheet.
Exactly. Or you'll say, "Love you, bye," to your boss on the phone. The wires just get totally crossed.
It is basically the universal human experience of your brain just running out of RAM.
Yeah, but here is where it gets interesting, because we aren't here today to talk about human productivity.
Thank goodness.
Right. We are here to talk about why we keep forcing artificial intelligence to do that exact same multitasking thing, and then we all act totally surprised when it completely fails.
It's a huge issue right now.
It really is. So for today's deep dive, we are looking at a really fascinating piece of source material. It's an article by Aaron Rose titled "The Secret Life of Azure: Scaling with Multi-Agent Teams."
And this is a really significant piece of writing because it tackles the monolith problem head on.
The monolith problem, yeah.
Right. Because Rose isn't just talking about prompt engineering here. He's talking about fundamental software architecture.
And the way he frames it is great.
Yeah, he uses this narrative framework. He sets up a whiteboard session between a very frustrated engineer named Timothy and a senior architect named Margaret.
I really appreciated that narrative device. It grounds all the heavy technical theory into a very real, very relatable office crisis scenario. You can practically smell the dry erase markers.
For sure.
So our mission today is to essentially deconstruct that whiteboard session. We need to understand how we move from having one single overworked AI brain to a coordinated team of specialists.
And I'd say more importantly, we need to understand why that specific shift solves the hallucination problems that are currently keeping engineers up at night.
Exactly. So let's just set the scene for everyone. We have Timothy. He is standing at a whiteboard, and it's just covered in red and blue marker ink.
He's stressed.
Very stressed. He is building what he calls an LLM reasoning engine, and he is hitting a massive wall. What exactly is the technical bottleneck he's facing here?
Well, Timothy is trying to build a system that handles a composite workflow.
Okay, composite meaning?
Meaning it has to do a couple of different complex things in one sequence. Specifically, his use case is that the AI needs to ingest a messy, unstructured file.
Like a PDF or something?
Yeah, maybe a PDF or a scanned image of an invoice.
Yeah.
It has to extract very specific data points from that mess and then immediately update an inventory database using an API.
I mean, on the surface, that sounds like a standard Hello World application for modern AI. Read this thing, update that thing. Why is he struggling so much with it?
The problem is how he's instructing the AI. Timothy is trying to do all of this inside a single context window.
Just one massive prompt.
Exactly. He is shoving the OCR instructions, all the text analysis logic, the strict SQL schema, and the database update rules all into one prompt for one single agent.
Okay, let's pause on that for a second, because we hear about context windows all the time, usually just as a measure of how much text an AI can hold in its memory at once.
Right, the token limit.
Right. But you are suggesting it's not just about running out of space, it's about interference.
Precisely. It is about cognitive overload for the model.
Yeah.
Think about how the attention mechanism in a transformer model actually works.
Okay.
It attempts to attend to relevant tokens to predict the next word. When you have the messy, sprawling text of a source file sitting right next to the highly structured, rigid logic of a SQL schema in the exact same window,
you create noise.
Massive noise. The model just gets distracted. It might pull a random digit from the text and try to execute it as a database command.
Oh, wow.
Or it might completely hallucinate a column name because the text happened to mention shipping dates.
So it isn't just forgetting things because the window is too small. It's context contamination. The ideas are bleeding into each other.
Correct. Timothy describes it to Margaret as the system literally falling apart. The agent starts mixing up its instructions. It hallucinates.
And when you are dealing with a database that controls real-world inventory, a hallucination is not just a quirky, funny, wrong answer.
No, it is a data corruption event.
Which is a nightmare. And that brings us to Margaret. So the senior architect walks in. She looks at this chaotic whiteboard, and she diagnoses the problem immediately. She tells him, "You're treating the AI like a monolith."
Which is such a great phrase.
It is. Now, in traditional software development, if someone calls your code a monolith, it usually just means it's one giant code base that's super hard to update. But what does she mean here in the context of large language models.
She means Timothy is asking for a general intelligence solution to solve a highly specific engineering problem.
Ah, I see.
By asking one single agent to be the reader and the data analyst and the database administrator all at once, he has created a single point of failure.
Because it has to be an expert in everything.
Right, and it's non-deterministic. Every single time he runs this monolith, the interference pattern in the attention mechanism might be different. Sometimes it works, sometimes it corrupts the database.
So Margaret essentially wipes the whiteboard clean. She says, we need a new architecture. What does she draw?
He draws a tree structure. At the very top, there's a single box, and down below it, two separate distinct boxes.
Okay, a tree.
Yeah, and this is the classic visual representation of a multi-agent system, or what we call a MES.
MAS, right. Let's break down that bottom layer first, the two boxes at the bottom, the specialists.
So Margaret calls this concept domain isolation. Instead of one agent doing everything, she proposes two totally distinct agents. You have Agent A, which is the extraction specialist.
Okay.
Its entire universe, its entire prompt is focused solely on OCR and text analysis.
So it's just reading the messy PDF.
Exactly. It knows absolutely nothing about databases. There's no SQL. It doesn't even know what an API is.
And then Agent B.
Agent B is the inventory specialist. It is initialized purely with the database schema and the specific API tools needed to update records.
But it doesn't know how to read.
Right. It has no idea how to parse a PDF. It doesn't even know what optical character recognition is.
I want to really push on this concept of domain isolation for a second because it seems crucial. Aside from just being a neat and tidy way to organize code, what is the actual functional benefit here? I mean, if Agent A is smart enough to extract complex data from a PDF, why can't we just trust it to update the database too?
Because of the blast radius of potential errors.
Blast radius.
Yes. Think about it. If you have a monolith and it misinterprets a stray line of text in that PDF as a command to drop a database table.
Oh, because it has all the tools at its disposal.
Exactly. It has the tool access to actually execute that destructive command.
Yeah.
By isolating the domains, you are applying the classic security principle of least privilege.
So you're putting up a firewall.
A functional firewall, yeah. The extraction agent literally cannot corrupt the database because it does not have the API key. It doesn't even have the function definition to talk to the database. It creates a hard safety rail.
So even if the extraction agent goes totally crazy and hallucinates wildly and says the inventory is 1 million units of bananas, it can't write that to the database.
Right. It can only output text. It contains the chaos to just that one step.
Okay, that makes perfect sense. But this immediately raises the big objection that Timothy brings up in the source narrative. And honestly, it's the very first thing I thought of too.
How do they talk to each other?
Exactly. If Agent A and Agent B are totally isolated and they don't even know the other one exists, how do we actually complete the workflow? Haven't we just created two disconnected silos?
And that is exactly where we move to the top of the tree Margaret drew. That single box sitting above the specialists. The orchestrator.
The orchestrator. It sounds very managerial.
It is a manager.
But let's get technical for a second. Is this orchestrator just another LLM prompt? Or is it hard-coded logic?
It is usually a hybrid of both. But its primary function is logic and routing, not execution. Margaret explicitly describes the orchestrator as the decider, not the doer.
The decider, not the doer. So it doesn't touch the raw data itself.
No, it doesn't do the heavy lifting. The orchestrator does not run the OCR model. It does not write the SQL query. Its entire job is task decomposition.
Breaking things down.
Right. It receives the initial request from the user, say, here's a new vendor file, update our stock, and it breaks that big request down into a logical step-by-step plan. Step 1, call the extraction agent. Step 2, validate the extracted data. Step 3, call the inventory agent.
But wait, I have a question here. If the orchestrator is an LLM itself, doesn't it suffer from the exact same context window problems we just talked about with the monolith? Why doesn't the manager get confused?
That is a great question. The difference lies in the density of the context. The orchestrator is not loaded down with the raw text of the Victorian novel or the massive schema of the database.
Oh, so its prompt is much smaller.
Much smaller and much lighter. Its context only contains high-level descriptions of the tools it has available. It basically just knows, I have a tool that extracts text, and I have a tool that updates inventory.
It's operating entirely at a metadata level.
Exactly. It is like a general contractor building a house. The contractor knows that the electrician handles the wires and the plumber handles the pipes. But the contractor does not need to memorize the exact part number for every single copper fitting.
That makes a lot of sense. And because that prompt is so much cleaner, the LLM's reasoning is going to be a lot sharper.
Right. It can focus purely on the sequence of events without getting distracted. It just says, okay, extraction agent, you go first. Give me the results.
Which brings us to the part of this whole architecture that I think is the real secret sauce. And frankly, it's the part that usually breaks in these systems if you aren't really careful, the handoff.
Yes.
Timothy asks Margaret, how does the data actually get from point A to point B?
And Aaron Rose uses a great analogy here. He calls it a relay race.
It's a classic analogy, sure. But let's drill down into the mechanics of that. What exactly is the baton being passed?
The baton is shared state. And we need to get very specific here because shared state can mean a lot of different things in programming. In this specific multi-agent architecture, we aren't just talking about one agent whispering a sentence to another agent.
Right.
We're talking about a highly structured data payload. Usually, that is a JSON object.
Okay, so Agent A, the extraction specialist, finishes its job. It doesn't just shout the raw text answer out into the void.
No. Agent A processes the messy invoice. It carefully extracts the SKU number, the item count, the delivery date, and then it formats all of that information into a clean, structured JSON output.
And it drops that JSON into the shared state.
Yes. Think of the shared state as a central memory board or a log file that the orchestrator actively manages.
And does the orchestrator just pick up that baton and blindly hand it straight to Agent B?
Ideally, absolutely not. And this is really the magic of the orchestrator model. Because the orchestrator sits in the middle of this transaction, it can perform a validation step.
Ah, validation.
Right. It can look at that JSON object sitting in the shared state and ask, does this actually look like a valid inventory update?
So it acts as a quality control gate before anything else happens.
Yes. Before it even wakes up Agent B, it checks the baton. If Agent A returned total garbage or a hallucination that doesn't match the expected schema, say it put a date where a number should be, the orchestrator catches it right there.
And what does it do then?
It can say, hey, Agent A, you messed up the format, try again. Or if it fails too many times, it can flag an error and escalate it to a human.
That is a huge fundamental difference from the monolith approach. In the monolith, if the model hallucinates a bad command, it just fires it off. It just happens.
There are no breaks.
Right. But here, we have a hard checkpoint.
Exactly. Once that data is fully validated and clean, the orchestrator hands a sanitized JSON baton over to Agent B.
And this is exactly why Agent B doesn't ever need to know how to read a PDF.
Correct. Agent B never sees the messy source file. It never sees the Victorian novel. It only sees a pristine, deterministic instruction that says, update SKU 123 with quantity 50.
That totally eliminates the interference problem we talked about at the start. We have effectively cleared the context window for the second agent.
And that is the core technical victory of this whole setup. By sanitizing the inputs for every downstream agent, you remove the noise that causes hallucinations. You are literally turning a stochastic, probabilistic guess into a deterministic, reliable database transaction.
Turning stochastic guesses into deterministic transactions, that really ought to be the tagline for enterprise AI right now.
It really is the ultimate goal for anyone building these systems.
So let's go back to our narrative for a minute. Timothy is standing there. He is looking at this new diagram Margaret drew. He sees the orchestrator at the top, the specialist below, and this very clean shared state flow connecting them. How does he react to all this?
Well, the relief is pretty palpable. He realizes that Margaret hasn't just given him a quick hack to fix a bug. She has given him a complete architectural shift.
Right.
He makes this really profound observation in the text. He says that this is no longer just an agent. It is now a distributed system.
And that is a very heavy term in computer science. Distributed systems are notoriously difficult to manage. I mean, are we just trading one set of annoying problems for a different set of problems?
In a way, yes. But we are trading unpredictable problems for predictable complexity.
Okay. Explain that difference.
Well, yes, a distributed system has a lot more moving parts. You have to manage the network handoffs, you have to monitor the orchestrator's logic. But as Margaret points out to him, this architecture finally has room to breathe.
Room to breathe. What does she mean by that, practically speaking?
She means scalability and debuggability. Think about it. If the data extraction step fails today, you know exactly where to look. You go straight to Agent A.
You don't have to sift through the database logic.
Exactly. You don't have to tear apart the entire massive prompt. And it means you can swap out components safely. If OpenAI or Anthropic releases a brand new, vastly superior OCR model next week, Timothy can just update Agent A to use that new model.
And Agent B doesn't care.
Agent B and the orchestrator don't even need to know what happened. As long as Agent A still outputs that same valid JSON baton, The system keeps running smoothly.
Modularity.
Pure modularity. It allows you to upgrade and maintain the system piecemeal.
That is a massive advantage for any engineering team. But I want to play devil's advocate here for a second.
Go for it.
We have painted a very rosy picture of this setup. The manager at the top, the workers diligently doing their isolated tasks at the bottom. But in the real world, and certainly in computing, managers can become massive bottlenecks.
Oh, absolutely.
If the orchestrator is suddenly responsible for every single decision, every routing call, every single validation step, doesn't the orchestrator just become the new monolith?
You have hit on exactly what we call the centralization paradox in MAS. Yes, the orchestrator is a single point of failure. If the orchestrator's model goes down, or if its routing logic gets stuck in a loop, the specialists are just sitting there doing absolutely nothing.
And what about the speed? What about latency? We're adding multiple network round trips here. The user talks to the orchestrator talks to agent A replies back to the orchestrator, then to agent B.
It is significantly slower. There is just no getting around the physics of that. A monolith, if it actually works, is one single shot, bam, done. This relay race takes time.
So it's trade-off.
A huge trade-off. You are explicitly trading latency for reliability. Now, for an inventory system running in the background, that is a fantastic trade. A few extra seconds don't matter.
But for a real-time voice chat bot?
Maybe not.
Like
The latency might be unbearable for a user. You have to really know your use case.
Okay, but there is another risk here that I think is perhaps a bit more subtle. We are essentially building computer systems that mimic human corporate teams. And human teams have, well, they have politics.
Yes, they do.
Are you telling me my AI agents are going to start gossiping at the digital water cooler?
Not gossiping, but they definitely start deadlocking.
Deadlocking.
Yeah. Imagine the orchestrator tells Agent A to extract a date. But the date is blurry, so Agent A needs clarification. It politely asks a question back to the orchestrator.
But the orchestrator isn't expecting a question.
Right. The orchestrator was expecting a JSON object. So it gets confused, and maybe it forwards that question over to Agent B, who only knows how to write SQL. So Agent B throws an error back to the orchestrator.
Oh, no. So they just get stuck.
Infinite loops. You can very easily create situations where these brilliant agents are just politely passing the baton back and forth forever, because no one has the actual authority or the clear instruction to just stop and say, we failed.
So we need managerial oversight for our AI managers.
We really do. We need strict timeouts. We need loop detection algorithms, and we definitely need human-in-the-loop escalation paths. We cannot just set these multi-agent teams loose and assume they will always play nice.
That is a really crucial point for anyone listening who's building this stuff. Just because it is labeled AI does not mean it manages itself. It actually requires more rigid structure from us, not less.
That is the great irony of all this. To make AI behave creatively and intelligently on complex tasks, we actually have to put it in a very strict box, or in this case, a series of isolated boxes connected by a very rigid manager.
So as we wrap this up and zoom out from Timothy's whiteboard, we've gone pretty deep into Azure, into JSON payloads and transformers. If you're a listener sitting there right now, maybe you're a developer or maybe you're just a tech-curious project manager, what is the primary takeaway from Aaron Rose's piece?
I think the biggest takeaway is that basic prompt engineering is dead. AI architecture is the future.
Wow, that is a bold statement.
I believe it's true. The era of trying to whisper the absolute perfect magic spell into one single giant omnipotent brain is ending. We are officially entering the era of building reliable modular pipelines.
Yeah.
Whether you build them on Azure or AWS or locally on your laptop, the core principles from this deep dive domain, isolation, shared state, and orchestration, those are universal.
It's about building a competent team, not trying to build a god.
Beautifully put. A well-coordinated team of narrow specialists, guided by a very clear process, is always going to beat a solitary genius who is desperately trying to do 20 things at once.
And they are far less likely to accidentally delete your entire production database.
Definitely less likely.
I want to leave everyone with a final thought to mull over. We talked earlier about the orchestrator potentially becoming a bottleneck and agents getting stuck in polite little loops.
Yeah.
If we keep scaling this multi-agent philosophy up, teams of AI teams, AI managers managing other AI managers, are we ultimately just recreating human corporate bureaucracy inside our servers?
It is entirely possible that we are currently building the world's most computationally expensive digital middle management.
On that slightly terrifying note, we will leave it right there. A huge thank you to Aaron Rose for the original source material, The Secret Life of Azure, Scaling with Multi-Agent Teams, which sparked this whole analysis. We are not endorsing any specific vendor, just exploring the ideas he laid out.
It has been a real pleasure deconstructing it today.
And thank you for joining us for this deep dive. Remember, stay in your lane, always validate your JSON inputs, and for the love of clean code, do not let your SER agent touch your database. See you next time.